So, what we need is something very obvious, which is what we have been sort of alluding to also. We cannot search till the leaf. We have to stop in the middle, be it depth 4, be it depth 8, whatever it is, but we have to stop in the middle. And that algorithm is called minimax with cutoff. So, depending upon how much you can see, even if you play chess or any game, what do? You think about, if I move my pawn, then the opponent will move their bishop, and then I will have to move my this, and then they will do this, and at some point it is too much for you. So, you stop, and then you say, okay, this is how it looks like when I move the pawn. Well, what if I move my king? Then how does it look like? So, with every move you think a little bit about how the future is going to look like. You do not go till the very end of the game. You do not analyze all possibilities for you and for the opponent, for you, for the opponent till the very end of the game, and then make a decision. You say, okay, when I do this, I might be able to capture that, so that looks like a good move to me. That is it. You do some sort of shallow reasoning, and how much you are able to look in the future determines how good a player you are. For example, if you do only 4 ply, then you are a human novice. If you do 8 ply, you are like a human master. And this was the typical PC 20 years ago. And then if you do 12 ply or 14 ply, then you get to Kasparov and Deep Blue level. And now today all the chess players are like much better. Right? So, our point is, well, we are not going to be able to the very end of the depth, we are just going to cut it off in the middle. And you will have to do it, because we just cannot get to the end, too much. But of course, now the question is, what path has raised? The question is, suppose I only search till this point, what do I back up? What do I back up? Eventually, I know nothing about anything. I have not reached the end of the game. If I have not reached the end of the game, I am stuck. What do I do? And the intuition is going to be, or sort of the answer is going to be what Jay has already given. We will allow our search to stop in the middle, and we will think this is leaf, but we do not know who wins or who loses. So, we will somehow evaluate whose position is strong, me or my opponent. In the leaf, or this artificial leaf somewhere in the middle of the node, we will define an evaluation function that evaluates this board position and says, at this point I think that you, the computer, is this much better than the opponent. And this is going to be the key to making any game playing agent. Okay. So, we are going to call it evaluation functions. For example, if I want to do tic tac toe, now of course tic tac toe is a very simple game, boring game, you can even search till the very end, but suppose I stop in the middle and I want to predict who is going to win or whose position is stronger. What may be a simple way to achieve this? Well, let us say I define this idea that I will count the number of rows, columns and diagonals in which the computer can win still, and number of rows, columns and diagonals in which the opponent could win still, and then take a difference and say that is my evaluation function. So, for example, if I give you the first board position, then for computer cross, how many ways in which it can win? It can win in one diagonal and two diagonal. It can win in this horizontal position and another horizontal position. It can win in this vertical position and another vertical position. So, how many ways can it win? 6. But for not, how many ways can it win? No diagonal. It can win in one horizontal and two horizontal. It can win in one vertical and two vertical. So, in this case, which looks stronger? The cross looks stronger, and looks stronger by let us say 2. Now, this is a evaluation function, I can multiply everything with 20, I can multiply everything, add everything with 10, whatever, it does not matter. It is some notion of how much stronger the computer is versus the opponent or vice versa. So, this way I have, what have I done? This is actually important. What have I done? I brought out this idea that the number of rows, columns and diagonals in which I can win minus the opponent can win is a good property to have in the board. Where did this idea come from? This idea came from my pocket. I looked at the game, I thought about the game, I analyzed the game and I said, okay, this is a good property to have. This property came completely from my pocket. And now I told the computer that this is a good property. Use this as an evaluation function. This property will determine the evaluation function of that point. And I will use that to back it up. Is it a well formed setup now? Does that make sense? So, just to repeat, this is actually important and this is the most important part of today's lecture. So, I am doing minimax search with alpha beta pruning and I do a cutoff. I stop somewhere in the middle. I cannot search further, I do not have the time. At that point, I have only a partial board position, I have not reached till the end. I will evaluate this partial board position. How would I evaluate it? I will come up with some property of the domain which says whether this board position is in my favor or in the opponent's favor and how much, and that will be the value of the leaf. And then I will back it up. So, at the top I will be taking that action which maximizes the utility function of the point of cutoff, and the utility function will be defined by me. But of course, it is very hard for me to define a utility function for every state. For a game like tic tac toe, it might work out, but let us say I am giving you a game like chess. How would you do it? So, there the traditional way, and there is a modern way also, which we will come to towards the very end of the course. But the traditional way is that I do not come up with one property of the board, I come up with many properties of the board. How many queens do I have? How many pawns are near queening? How many of my pieces are getting attacked? How many pieces do I have? How many pieces does my opponent have? How many bishops do I have? How many bishops does my opponent have? Etc., etc., etc. I define all of these what we call features. Where do these features come from? They come from my pocket. This is very important. So, I define features. For example, one feature would be number of white queens minus number of black queens, if I am white. This is a feature. Now, I will define many such features. Let us say I define 50 features or 100 features like this. Now, my goal is to define the partial, a board configuration, and for each board configuration, each feature will have some value, like number of white queens minus number of black queens may be 0, number of white bishops minus number of black bishops may be 1, etc., etc., etc. Number of white pawns minus number of black pawns may be minus 2, feature can be negative, the opponent has more pawns. Now, in this situation, I need to somehow consolidate all these feature values and create one function, which is what we are going to call the utility function of the stopping point, intermediate board position. How do we do that? And as a simple starting point, we will take a weighted sum of all the feature values. So, my evaluation function would be W1 F1 plus W2 F2 up to Wm Fm if m are the number of features, and these Wi's are the weights of each feature. It is the importance of each feature. For example, number of white queens minus number of black queens is a very important feature. Number of white pawns minus number of black pawns, important, but not as important as number of queen difference. If I have 2 queens now and my opponent has only 0, I am like super strong, whereas if I have 2 pawns less, I am weaker, but not by as much weaker as if I had 2 queen difference. So, W1 would be much higher, W for the pawn would be much lower comparatively. So, now we have done this division of labor. The human, the domain designer, the game developer has defined all these features and has defined a representation, the linear sum of basis. So, this is also called the sum of basis function representation. Each of these features sometimes also called a basis function, does not matter, these are different terms for the same thing. So, I have now defined all these features, now I need to somehow compute the weights. So, now we have, whenever I am in this setting where I have to learn something from data, that is where we get into machine learning. So, we did sign up to study machine learning in this lecture, but this is a bonus, we are going to study machine learning, because until we study some machine learning, we will not be able to complete the story of game playing. And there is a full field which does this, called machine learning. It is now a very famous, very popular, very influential field. There is a full course on machine learning that you should do after you do the AI course. But for now, without going into all the details, I am going to give you the flavor of how these things work. Okay? So, for example, the very first time some of these ideas were used were in Samuel's checker playing program. Now, Arthur Samuel was a researcher at IBM. In the 50s, he created this checker playing program and he used machine learning. In fact, he is credited to coining the term machine learning. We earlier told you who coined the term artificial intelligence. Arthur Samuel, who created the checkers program, coined the term machine learning. He may not have known that it will become that important today. So, for example, we are looking for an evaluation function which is like something like 6k plus 4m plus u, where this is checkers parlance, not everybody may or may not, not everybody may know checkers, but 6 times k advantage plus 4 times man advantage plus u times undenied mobility advantage and so on. So, this is what we are looking for. We have defined k, m and u as features, we are now looking for 6, 4 and 1 as the weights of that. So, how do we do that? And we are going to do that by experience, we are going to do that by playing. Okay. So, what is going to happen is, let us say we have some initial value of the weights. If I have initial value of the weights, I can play the game now, I am done, right. I can just play the game using those value of the weights, but I can't play because I need an opponent. So, let us say the opponent also has the same values of the weights. So, let us say now I have some values of the weights and I have 2 game players for those particular weights, let us call them A and B. Now, B is going to be fixed, A is going to be learning. Okay. This is important stuff. If you have any questions, feel free to stop me and make sure that you understand this. So, what is happening is that I have some weight values for each feature. If I have a weight values, then I can compute the evaluation function at every node. If I can compute the evaluation function, I can do minimax, alpha, beta, pruning and cutoff, and I can search and I can decide which action to take, which move to take, and I can play the game. So, basically I have completed my game player. And let us say I make 2 copies of this game player, A and B. Let us say B is going to be stay fixed. B will not change. A, however, is going to learn against B, and what does learning mean? Update its weights, very good. And for most of modern machine learning, learning basically means update weights. You may have millions of weights in the most modern world. In this small case, we may have 3 weights or 10 weights, but learning for most modern machine learning is learning weights. So, what is going to do is A is going to adjust its coefficients after every move, and how is it going to adjust its coefficients? Okay, that is very important. And again, I am going to just give you the sort of post basic core. So, intuitively Suppose f1n is positive. When should I increase W1? I should increase W1 if initially I thought this board is good, this position is good, but it's actually even better. That's the intuition. I have initial idea of how good this board is, and then I did some play and I get a better idea of how good this board is. And suppose this new idea of how good this board is says that this board is better than what you originally thought it to be, I am going to increase the weight of all the features which are positive, and I am going to reduce all the weights of features which are negative. That is it. So, you are sort of going to do Wi is equal to Wi plus or minus some learning rate, some difference, some delta. That is what you have to do. This is the core of all machine learning. Then the only question is how do you compute how much you increase it or decrease it by, and then people do gradient descent and this, that and the other, right. But essentially all Wi is equal to Wi plus something, and that is all update equations in all of machine learning. So, coming back, now the issue is how do I know what was my original board positions value and how do I estimate a new value? Make sense? Now, you know how to estimate the old value. What is the old value? What is the old value? Look, I already have some Wi's. For every board position I can evaluate the Wi Fi summation. So, I have some Fi, Fn for that board position. So, this is my original board positions value, original value of the board position. Now, what am I going to do next is I am going to play the game up to some cutoff, backtrack and compute the best value based on this look ahead search. Okay. So, this is important. So, what do I do? Initially I came to this node, I say this node looks as good as 20 based on my current weight values. Then I started playing this game up to, let us say, depth 5, whatever, right. I did this, I backtracked. Now, at the depth 5 I am still using the same evaluation function, it is not like I am using something very different. I use the same evaluation function, but now I am backtracking these values and finally my original node which had value 20, let us say has value 30. So, now what do I need to do fundamentally? I need to move my weights such that this 20 moves in the direction of 30. So, the initial value of the node is the original f value and the backed up value of the node is the value that I used with minimax and cutoff and this evaluation function at the cutoff point. If this delta is greater than 0, then all the terms that were contributing positively to me, all my features which were positive, their weights have to increase, and all the features that were negative, their weights have to decrease. On the other hand, after backing up, I get no, this is not 30, it is actually 10. Earlier I thought it is as good as 20, but now it is as good as 10. That means I need to reduce the value of my node. That means all the features that were contributing positively, their weights need to go down, and all the features that were contributing negatively, their weights need to go up. How much they go down, how much they go up depends upon how much delta is and what is the learning rate. How quickly do I want to move my weights? Usually learning rates are not kept very high, they are kept low so that I sort of average it out over time and over different nodes. This is the main idea of machine learning in the context of gameplay. And in the previous generation of AI and machine learning systems, all the features came from our pocket, but in the most modern version, features are not given by humans, The machine learns the features, and this they do by deep neural networks, and we will talk about that towards the end of the course. Questions?
Isn't it all possible that with the new weights, now again if you evaluate with the same depth, it actually goes against the trend that you were expecting?
Yes. So, the question is it possible that at this intermediate point when I did some learning, I have gone in the wrong direction? Yes, it is possible, because it is not like this is sacrosanct, right, because even at the end of cutoff I am still using this evaluation function to evaluate, and I am only playing against this fixed B. Now, this particular opponent may have weaknesses. I may learn to exploit those weaknesses and start to think that, oh, this board position is really good because in this board position I can exploit my opponent's weakness, but that is not going to give me the best gameplay. So, how do we fix that problem, by the way? Very good. What's your name? Divyansh says, if I get a better A, at some point I make A the B and restart. This is what it says here. If A wins, if I am actually making progress, if I am improving my value function, if I am improving my evaluation function, at some point you say, look B, you were good for making me learn, but now you are a crappy opponent. I have really learned so well that I don't want to learn against you. And so, I mean, in practice, in human world, we will say, look, you opponent, you go improve your game, I will play this better opponent so that I improve my game. In the context of game playing, I become the opponent and somebody else is being developed which is better than me, right. This is slightly different, but it is the same idea. I would not want to play Roger Federer in lawn tennis. I can play my mom though. I am a terrible player. So, that is the point, right. So, you want to always play to a point where you can learn something more, and after that the opponent is not useful very much in learning. So, that is exactly what you do. You start with A and B. Once you have a better A, you make that B and you create a A which is better than the new B, which is the old A, and you repeat this process and you keep doing this, and the more you do this, the better your evaluation function gets, and the better it gets, you get a better game player. Yes.
When you start at the root node and you go to, let's say, the 5th level and you have the same evaluation function throughout, then levels 1 to 4, do they make any difference, or are they important at all?
Right. So, the question is that if I go till the depth 5 and then I have an evaluation function at the depth and then I back it up, what happens to levels 1 to 4? Well, you are also getting some insight about 1 to 4, because even for 1 to 4 you had some evaluation function and you have some backed up value. In that case, your backed up value is less than 5 depth, it is 4 depth or 3 depth or 2 depth, but you can still use it to improve. Maybe you will trust it less because the look ahead was less, but see, this is essentially internal consistency property. It is saying that whatever WIs you get, it should be such that whether you back it up or you evaluate at the top, the difference is very small. It is almost the same thing. It is internal consistency, but then you play against it and you improve it further. So, this is how the world works. There are many tricks that you can use. For example, you play the game till the end, do not back up anything, but then start backing up in the reverse direction, because at the end you are getting some real information about who won the game, who did not win the game. So, you can back it up. You can also do some kind of exploration step. In this exploration step, sometimes your opponent will take a random action. That way, you will not be playing against a very fixed deterministic opponent, you will be playing against slightly stochastic opponent. That way you will become more robust to different kinds of opponents, etc., etc. So, there are lots of tricks of the trade that one can develop this, and as we go into the topic of reinforcement learning, we will discuss some of those ideas as well. Any other questions? We should stop. Thank you.